Hello everyone, welcome back. So this is a new series that we are trying to start. In this series, we will be covering one topic every alternate Saturday. Basically, the one which doesn't have the bi-weekly contest. So that's the plan right now. So I created a poll, and most of you guys said that we should start with segment tree. So this is the first video in the series of segment trees. Here we will be covering the basic segment tree, what it is, how to use it, how to build it, when to use it, and stuff like that. So by the end of the video, if even if you don't know anything about segment tree, I can assure you that you will understand what segment tree is, how to build it yourself, and you will be able to code it yourself as well. So stay tuned till the very end. This will be interesting. And with that, let's get started. So before jumping into segment trees, let's try to solve one smaller problem. So the problem is we are given an array and we need to find the sum in the range L to R, right? So this is very standard problem, and we have discussed many times the solution of this in many times in this particular channel. So pause the video, try to think it yourself if you haven't heard of this problem at all. Now hope you thought about it. So we need to find the sum in the range L to R. So the solution is simple. Basically, we will only maintain the prefix sum. So you'll say, okay, we know what is the sum up to index 1. We know what is the sum up to index 2. We know what is the sum up to index 3, and so on and so forth. Now, once we once we have asked that, okay, find me the sum between L and R, what we can simply do, we already know the sum of index up to R, right? So we already know the sum up to this index. We also know the sum up till this index, right? So what we can simply do, we can subtract this sum from this sum, right? So if we do this, we know we will be getting what is the sum of this particular range of numbers, right? So that's the idea. The if you see and like let's try with an example. Let's say this is this was the array, so we will build the prefix sum array. So we say, okay, sum up till index 1 is 3, sum up till index 2 is 4, sum up till index 3 is 10, right? Now how we are building this, we know to get the sum up till index 3, we can simply say what is the sum up till index 2 plus this particular index, right? So that's what we are doing. Like we calculated the prefix sum array. Now, once we had the prefix sum array, we can simply find out the sum between L and R, right? Now, let's modify the problem. The problem is now, apart from this query of L and R, we are also given a query of the form I comma v, where this query says that update index I or update the value of index I to a new value v. Okay, so let's take an example. So this this query can mean that, okay, update this particular index with, let's say, 10, right? And we are given these queries and these queries in interleaved fashion, right? So for example, the queries can be of the form this L comma R, I comma V, and then L comma R, then I comma V, and then some L comma R, and so on and so forth, right? Now if you think about it, you can't actually apply the same algorithm here because the values here are changing. So once a value change, you know you have to update the prefix sum of everything after that, right? So basically this index, the prefix sum up till this index contains everything up to this particular index, right? So now if this particular value changes, the prefix sum up till this index will change, prefix sum up till this index will change, and so on and so forth, right? So every operation of this kind would incur us order and cost, right? So basically we can use or answer these two queries in an efficient manner. So that's where the need of segment tree comes, right? Again, there are various other issues with the solution that we just discussed. Basically, we are able to query the sum in the range L2R. But let's say you have to find the maximum number in the range L2R. You can't do this. The sum one, you can do this because you know that sum is cumulative. Basically, whatever sum, if you have to find the sum of this, you know, you can simply find the sum of this and subtract it from the entire sum. But the same trick you can't apply if you have to find the maximum. Let's say you have to find the maximum of this L2R. You can't say that, okay, I will find the maximum up till index R, I will find the maximum up till index L, and I will do something uh, with these two numbers to get the maximum in the range L2R. That is not possible. So that's like various places where segment tree can help us. So any range queries, segment tree will be able to help us. Like most of the range queries, segment trees will be able to help us, right? So with that context, let's see how to actually build a segment tree, right? So we are taking the same example. We have to answer the queries L to R, basically sum in the range L to R, and we also have to answer the queries where given the index I, update its values to B, right? So let's take the same array 316048552. So how segment trees looks like is each of these array values would be the leaf node of the tree. So each of these value will just put at the leaf, right? Now from each of these two nodes we will build one parent node. So from 3 and 1 we build one node, from 6 and 0 we build one node, and so on and so forth. We will keep on doing this until we reach a single node. So basically from these two nodes we'll again build one more, from these two nodes we'll again build one more, and from these two nodes finally we build one more node and get the root node. Now each of these intermediate nodes we will store some property here. Now one interesting thing about each of these nodes are they represents a range of the array. For example, this is the 0th index. So basically this represents 0 comma 0 of the array. Similarly, this is the first index. This represents 1 comma 1 of the array. Now this node covers these two nodes. So this represents 0 comma 1 of the array, right? And similarly, this node represents these four pieces, right? So basically, these nodes represent 0 comma 3 of the array, right? So every node represents one particular sub array of the original array, right? So that's how we build this tree. Now in each of these nodes we can store some property. Now the property that we will be storing will depend on the problem at hand, but for now let's try to just solve for the range sum. So we will just store the sum of like the sum of the values in this node. So for example, in this case this node represents summation of 0 comma 0 and 1 comma 1. So we just add these two values and say, okay, this node represents the value of this node is 4. Similarly, this here this node represents 2 comma 3, so value of this node is 6. We just add these two values, right? In the same fashion the value of this node would be 12 and the value here would be 7. Now again this node represents the sum of these two nodes, right? So the sum here would be 10, and in the same fashion the sum here would be 19, and finally 10 plus 19, 29 would be the value of the root node, right? Now this is what is called segment tree. Now forget about what it can do and how to use it the for solving the problem that we just discussed, like given a range, tell me the sum, or given the value, given the index, update its value. So forget about all those things. Let's just first focus on building this tree entirely. So let's say you have to build this tree efficiently. How exactly will you be writing the code to build this tree? So pause the video, think about it for a moment, and then come back. So one hint that we can like that I can give you here is, let's say we have to build the segment tree for this entire array, right? So this is the tree for this entire array. Uh, this is the tree, right? Now we can just divide the problem into two parts. We can say, okay, build the tree for the left half of the array, build the tree for the right half of the array, and then join these two to form a root, right? So that's how we are building the tree. So basically, we are given the problem to build this is the tree of this entire array. We divided the problem and say, okay, we will first build the tree for this array, and then we'll build the tree for this part of the array, and finally we'll merge this to build the to complete the tree for the entire array. So hope you can see the recursion here, right? So what we are saying here that, okay, if we have if we have asked to build the tree for L comma R, sorry. So if we are asked to build the tree for L comma R, we will first build the tree for L comma M, where M is the midpoint of L and R, right? Basically M equals to L plus R by 2. And then we will build the tree for the right half, which is M plus 1 comma R, right? And finally, after building these two tree, I will actually fill the value of the current node or value of the root, which will be the summation of the root node of the left, root node of the right, right? Basically, let's say we build this entire tree somehow, right? We build this entire tree somehow. Now, what we need to do? We need to just add a root, add these two links, and the val and figure out the value of this node. Now, value of this node would simply be the sum of the left and sum of the right. So that's what we are doing. So we first build the left, then right, and then value. So again, pause the video, try to code this particular thing yourself, and then come back. Again, I would strongly encourage you to at least give it a try and try to code this yourself before jumping into the next part of the solution, next part of the question. So the pseudo code for the same would look something like this. So what we are saying is that we have to build the tree for L comma R, and this is the current root, right? Now this is the base case where we are saying that, okay, if L is equals to R, it means this is exactly one index of the array, right? So if L is equals to R, what does it mean? It means that we are at the leaf node. We are the leaf node, and this leaf node denotes exactly one element from the array. So we don't need to go downwards. Instead, we will just copy this to this particular position. So that's what we are doing. We just copied the value of array I to the current root and then return from this entire function. Now, if that's not the case, as we discussed, we will build the tree for the left half. So we are building the tree for L comma M, right? And then we'll build the tree for the right half. We are building the tree from M plus 1 comma R. And then we are filling up the value of the root, which is the value of the left, the value of the root of the left half and the value of the root of the right half, right? So this is exactly what the pseudo code would look like for building this entire tree, right? Now, dealing with pointers is difficult. Like we are dealing with pointers here, and it is very easy to forget initialization of this root value here, right? So let's say you want to address root arrow left or root arrow right. So it can happen that this is null or this is null, right? So you have to handle those cases as well. So, and also if you have a pointers to even iterate over the tree, you need to write a recursion, right? So that's where we will not use pointers to represent this particular structure. Instead, we will use an array. So like if you have tried heap sort in your algorithms class, you might know already that we can represent a tree using an array. So that's what we will be doing here as well. So what we will say that this is the 0th index of the array. This is the first index of the array. This is the second index of the array. This is the third index, and so on and so forth. So this is fourth one, fifth one, etc. Right? Now, why we are saying that this is the 0th index, this is the first index, and so on? Why not say that, okay, this is the 0th index, this is the first index, this is the second index, this is the third index, and then like 4, 5, 6, and so on? Why this thing instead of this? So the answer is pretty simple. If we structure the array in this fashion, then we know that we exactly know how to find the left and the right child. So let's say you are at index 1 of the array, right? So you want to go to the left child. So going to the left child would simply mean that, okay, simply mean that I will do, let's say this is I, so I will do I cross 2 plus 1 and I will reach to the left child. Similarly, for the right child, I will do I cross 2 plus 2 and I will reach the right child. So this is true for every index now. Let's say this is 2. So 2 cross 2 plus 1, 5 is the left child, 2 cross 2 plus 2, 6 would be the right child, right? Similarly, let's say, let's just expand this further. You want to find the left child of 3. So 3 cross 2 plus 1, 7 is the left child, 3 cross 2 plus 2, 8 is the right child. So basically, if because it is a complete binary tree, and if we structure our array in level fashion, like first this level, then this level, and this level, then we can deterministically determine the value of left and the right child easily, right? So that's where we will be organizing our array in this fashion. So we'll say, okay, 0 is my root, and then every node left child would be I cross 2 plus 1, and every node's right child would be I cross 2 plus 2. So that's the pattern we are following. And we we if we follow this pattern, this code would can be translated to this code easily. So what we are saying is, instead of taking a root, we will be taking an index, because we know that the actual node is a index of the array. So instead of root, we have taken the index. Now, instead of saying the value of the root, we are saying that what is there at that index, because this is now the actual node, right? Now this is the base condition, right? And for left and the right part, so instead of saying that root arrow left, what we are saying I cross 2 plus 1, because that's what the left child would be, the index of the left child would be. And similarly, I cross 2 plus 2 is the index of the right child. Now after these two, again, for getting the value of the left child, we will just access I cross 2 plus 1 of this array, tree array, and I cross 2 plus 2 of this tree array. So this will give us the actual value at uh, those two nodes, the left and the right child of the root, right? So this entire algorithm would actually build this entire tree very easily, right? So if you haven't understand this, again, strongly encourage you to rewind the video and watch this particular section again. Just to summarize what we have done, we have just built the segment tree, and we saw that this building segment tree follows a recursive property. That is, we want to build the segment tree for the entire array. We saw that we can divide this building into two half. We will build the segment tree for the left array, and then we will build the segment tree for the right of the array, and then we will just merge these two by adding the values of the root of the left and the right half. So once we have recognized this, we just wrote a simple recursion to build this tree. Now after that, we realized that, okay, dealing with pointers can be very tedious, and also um, it can be error prone as well. So that's where we converted our actual nodes or the pointers to a index in the array, and we choose index wisely, such that it always follows the property that left child is equals to I cross 2 plus 1 and right child would be equals to I cross 2 plus 2, right? Now I am not showing you why exactly this property is being followed here. You can take that as an exercise, because that would be overwhelming in the first for the people who are doing this for the first time. But if you want hints or in this context, I am happy to give you in the comment section. You can ask me. So Now, till this point, what we have done, we have built a segment tree. So we know how to build this structure, like how to build this segment tree structure, right? Now, before moving forward, let's try to calculate what is the time complexity of building this entire tree, right? And before itself calculating that, let's try to understand how many nodes will be there in this tree, right? So think about it. We have n nodes in the bottom, right? Because this is the, like this, each node here would represent one array index. So we have n nodes in the bottom, right? Now, just the layer above, we have n by 2 nodes because we have one node for every two node, right? Now, similarly, just a layer above, for every two node here, we again have one node. So for, like, we have n by 2 nodes in this layer. So in the next layer, we would be having n by 4 nodes, right? And we will keep on doing this until we reach 4, until we reach 1, that basically a single root node. Now, how many nodes would be there? Number of nodes would be n plus n by 2 plus n by 4 plus n by 8 up to 1, right? So this is a geometric progression, and this is decreasing progression. So if following the studies from 11 and 12, the value of this entire thing would be a by 1 minus r, where a is the first element and r is the actual factor by which the progression is decreasing, right? So a here is n, the first element is n, and r here is 1 by 2. So 1 minus 1 by 2. So this would come out to be 2n, right? So basically, the number of nodes here would be 2n, given n is the power of 2. So if n is not a power of 2, we will make it the make it to the nearest power of 2, and then number of nodes required will be 2n, right? Now, number of nodes is 2n, so that is fine. And we are, notice that we are actually visiting each node exactly once in this algorithm. So what we are doing is, once we reach bottom of the tree, once we hit the leaf node, we just populate it and then traverse backward. So we'll start with the root node. We will traverse each of these node. Now, once we reach leaf node, we will end our journey there, and then we will move upwards, right? And populate this part of the node first. Similarly, then we will move upwards and populate this part of the node first, and so on and so forth. So basically, every node is visited exactly twice. Once during the downward journey and once during the upward journey, right? So that's where this entire recursion would take order 2n time, right? Where n is the number of nodes in the entire tree, which in itself is 2n for an array of size n. So basically, this building of the tree would be order n complexity, and number of nodes also is in order n, right? So building this tree doesn't require much time. This is like the complexity here would is very similar to how we have built the prefix sum, right? So there is no problem here. Now, with prefix sum approach, we know that we are not able to do updates easily, right? We are not able to update a particular value, update a particular index to a new value easily, because that would lead to updation of all the subsequent indexes, right? So let's try to do updates here. Let's say the problem says that, okay, update index 2 from 6 to 8, right? So update this to 8. Now, which all nodes would be affected? Again, encourage you to pause the video and try to figure out exactly how many number of nodes would be affected. So given if there are n nodes in the tree, how many nodes would be affected if we update a particular value, right? So hope you have thought about it. So if you update this value, this node would be affected. So this will become 8, right? Now, if this node is changed, this node will also be affected. So this will become 12, right? Now, if this node is changed, this will be also affected, and this will become 31, right? So what we are seeing is every node that comes in the path of going to the leaf node of 2 is affected, right? Now, how many nodes would be there in this path? The number of nodes here would be the height of the tree, right? Now, what is the height of the tree? The height of the tree is log n. Now, why log n? Again, it can be derived with the same approach that last layer has n nodes because each of these nodes represents exactly mapped to one node of the array. Now next layer has n by 2 nodes and so on and so forth. So if you follow this progression, you will see that number of like the height of the tree is log n. So because height of the tree is log n, we know we need to traverse log n nodes to reach a leaf node. So if a node is updated, if the value of node is updated, we know that log n number of nodes, the value of log n number of nodes would be changed, right? So this is very efficient than the prefix than what we had in the prefix sum. So in the prefix sum, if the value of a node is updated, we have to update the value of all its following nodes. So for let's say if the value here was updated to 10, we need to update this node, and so on and so forth. We need to update everything in this range, right? So this was like updating order n nodes, and that's where the complexity was not good. But in this case, we what we are seeing is updating any node is just leading to update of order log n extra nodes, and this is efficient, right? Now, once we have updated a node, we need to update this tree as well. Like we have updated this 6 to 8, so we saw that okay, this become 8, this become 12, and this become 31. So how to write the code to update all these intermediate nodes as well for a single update. Again, this is also a very small, simple recursion. Pause the video, think about it. It would be very, very similar to how we have wrote this particular function, right? So hope you have at least thought about it. So the pseudocode for this would be looking like this. So what we will do, we have these two things, index and new value, right? And these three variables are exactly similar to what we had previously. So these three variables are required for the recursion, right? L and R would denote the actual ranges, right? And I would denote the index in the array because we are representing this tree inside an array. So I represent the index, L and R represents the actual range that we are that the current index is covering, right? So if L is R, it means we reach a leaf node, right? So if we reach a leaf node, we know that we need to update this leaf node to the new value. Now, why? Because we are sure that we will be following the path that would lead us to that exact node that we are trying to update. So if we are at leaf node, we know this is the index that we have to update, right? So once you have updated the leaf node, we will, let's say we are at some intermediate node. Let's say this is the node which we are at. So we will figure out where the index lies. Does it lie in the left half or does it lie in the right half? So if it lies in the left half, we need to go into the left half. If it lies in the right half, we need to go into the right half. Now, how to determine that? So what we have done, we have simply find the middle element, right? So middle element is 0 plus 3 by 2, which is 1. So we find the middle element is 1. Now we'll check whether the index we are trying to update is smaller than 1 or larger than 1. If it is smaller than equals to 1, it will lie in the left half. If it is greater than equals to 1, it will lie in the right half. Simple logic, right? So that's what we have done. So if index is less than equals to m, it means it lies in the left half. So what we are doing, we are going into the left half of the tree. So left half of the tree would be covering the range L comma M, and the actual index would be I cross 2 plus 1, right? Now, if that's not the case, we know that the index which we are trying to update lies in the right half. So we will go in the right half, right? So notice that either this or this would be executed. Now, after one of this is executed, let's say either we have gone into the left half or we have gone into the right half, we know one of this is changed, right? It doesn't matter whether we go into the left half or whether we go into the right half, we are sure that one of these is changed. Now, because one of these is changed, the value of this node will also be changed, right? So now what is the value of this node? The value of this node would be the new value of the left half and the new value of the right half, right? So that's what we have done. We have also updated the value of the current node with the sum of the values of the left half and the right half, right? So with this recursion, we will be able to update all the index which are, or all the nodes which are affected by updating a particular index, right? So again, just to reiterate, updating a node here, we saw that it will only lead to changes in login nodes. And to update all the nodes in this path, we just need to follow the path to the leaf, and we will update the value in the leaf and propagate that to the intermediate nodes while going upwards. So we update the value in the leaf, and then finally, after this entire thing is executed, we also update the current root node, right? So hope this point is clear as well. Now, what we know how to update, like how to build the tree. Building a tree requires order and time, and we also know how to update a particular value in the tree. And the like updating a value in the tree requires order log n time as well. Basically, this entire recursion would run in order log n time. Why? Because each time you are either going left or you are going right. So basically, if you are going left, you are skipping entire right half, right? So let's say initially you have total 2 n nodes. So initially you have, let's say, n nodes. If you are going either left or right, so in one skip you are skipping half of the nodes. So you now are left with n by 2 nodes. So you now left with only this part. So n by 2 nodes you are left with. Again, you will be deciding whether to go left or right, right? So from this n by 2 nodes, again you are skipping half of the nodes. So basically you go up to n by 4, and you will follow all the way up to leaf. So leaf would have one nodes. So you can see this has log n number of steps, right? So this is very similar to binary search or any geometric progression that you can look, that you might have done in your 11th and 12th classes. Basically, this would have log n number of steps, and because this has only log n number of steps, the depth of this recursion would be log n, and hence this entire recursion would run in order log n time, right? So now we know how to build a tree and how to update the tree in order log n. Let's finally look at how to query the tree, like how to query a range in the tree. So let's say we need to figure out what is the sum of the range 1 to 6, right? So this is L, this is R. We need to figure out what is the sum in this range, right? So how to do this? Again, the same trick will be applying. What we will say, okay, we need to find the sum in 1 to 6. So does 1 to 6 matches this 0 to 7? No. So let's go in left and right half both, right? So let's first start with the left half. So, okay, 1 to 6 matches with 0 and 3. Like 1 to 6, does it completely overlap with 0 comma 3? Answer is no. There are some, like there are some overlaps, but it is not complete overlap, right? So that's where we will again go to its left and right, right? So again, let's start with the left part, 0 and 1. So 0 to 1 and 1 to 6. So does they completely overlap? Answer is no. So we will again go to both left and right half. So again, let's first go to the left half, 0 comma 0. So 0 comma 0 and 1 comma 6. So does they completely overlap? No, but they do not partially overlap as well. So there is no overlap at all. So basically we know anything below this is of no use. So we will stop our search from here. Now we'll go to the next available path. So this is the right, we will now go and see the right path. So again, right path will check the same thing. The actual range is 1 to 6 and right path contain 1 comma 1. So does they completely overlap? Answer is yes. This node completely overlaps with what we are trying to search. So basically, whatever the value here would directly contribute to the range 1 comma 6. So we'll just add 1 to our result, right? Now we have completed our left half of 10. So let's go to the right half. So right half contains 2 comma 3. So let's see again. So the range was 1 comma 6. Right half contained 2 comma 3. So again, this 2 comma 3 completely overlaps with the range we are trying to cover, right? So that's where we will not go any deep. We will say okay, 2 comma 3 would be something which we need to consider. So we'll just add 6 as well to our result set. Now again, we have exploited all the like both left and right of 10. Let's so we exploited as we have covered the left half of 29. So now let's try to cover the right half. Same trick, 1 comma 6, right? So 1 comma 6 and this covers 4 comma 7. So 4 comma 7. So again, they don't completely overlap, but they don't lie like they have some partial overlaps here. So we know some of these nodes would be contributing, right? So we'll go again to the left and the right half, right? So we'll see, okay, what is 4 comma like now here it is 4 comma 5. So we will see, okay, 4 comma 5. So 4 comma 5 completely overlaps with 1 comma 6. So we know this will be contributing directly to our answer, right? So we will simply add 12 here and not go further down, right? So now after that we will cover the right half. Now right half has 6 comma 7. So again 6 comma 7 has partial overlap. So because it has partial overlap, we will go to this both left and right. So once we go to the left, we saw 6 comma 6. Now 6 comma 6 is a full overlap. We are trying to cover 1 comma 6 and we are at 6 comma 6. So this is full overlap. So basically this would be contributing completely to our answer. So we'll add 5. Now finally 7 comma 7. 7 comma 7 is completely not overlapping. So we will not go any more deep into this child, right? And finally the result that we have accumulated is our answer. So result is 1 plus 6 7 plus 12 19 plus 5 24. So you can see 1 plus 6 7 4 11 8 19 plus 24. So this is giving us the correct output. Now you might think, okay, this is much more complex and I don't think it would work. Like we have almost visited every single node, so I don't think that would be faster than order n. But the actual complexity of entire thing that we just did is just order log n. Now how? Let's look at it. It is very interesting. So we okay, let's start from the beginning, right? So let's say this was the tree and we are trying to find the sum in the range 1 comma 6, right? You can think of this entire exercise as finding out the leaf node of 1. So you can see if you try to find out the leaf node of 1, these all nodes would be coming in the path, right? Now let's say you have to find the leaf node of 6. So if you find the leaf node of 6, these all nodes would be coming in your path, right? So basically, everything in between is something that you will be considering, right? So if you go into the right path, you will be seeing that this is completely overlapping for sure, and you will not expand further. Similarly, for other nodes, let's say for this node, when you go left, you will see that okay, this node will be completely overlapping, and I will be not moving further downwards, right? So basically, this boils down to finding out the left node, finding out the right node, and we know that for all the nodes in this path, we will be not exploring the other half at all. So that's where finding one would require login time. So this would be login number of nodes, right? You will be visiting login number of nodes. Similarly, finding six or R would also require visiting login number of nodes. So in total, you are visiting two login nodes, or you are expanding two login nodes in the worst case. And because you are expanding only two login nodes, the entire complexity of this algorithm would be two login. That is, you will be adding up two login nodes in the worst case, right? So hope this complexity analysis makes sense. Just to reiterate, what we are saying is we will be either expanding left or will be expanding right. We will not be expanding both of them unless it is the first node in the order, right? So just to reiterate and take, let's take one more example. Let's say you have to find the sum in the range 1 or in the range 2 to 4, right? So you have to find the sum in the range 2 to 4. So again, let's try to apply the same trick. Find 2, so 2 would be here. Find 4, 4 would be here, right? So now you know that from 19, if you go to the right child, you will see that it is not overlapping at all, and you will not go further. Similarly, from 10, when you go to the left child, you will see it is not overlapping at all, and you will skip going down further. So basically, at the end, you are just visiting two login nodes and everything in between. And for everything in between, you are only touching the root node. You are not expanding it further, right? So hope the complexity analysis makes sense. Now, how to write the code? The code is very straightforward. Just to give you a glimpse, the code would have three conditions, exactly what we have just saw while doing the dry run. The three conditions would be either the node is partially overlapping, or the node is fully overlapping, or the node is not overlapping at all, right? So there are three cases. So if node is not overlapping at all, we know we don't have to do anything for that node. If node is fully overlapping, we know that we will take that node fully. If node is partially overlapping, we will go to its both left and right and try to see or trying to expand both, right? So again, pause the video, try to code it out yourself first. So this will also be a very simple recursion. So this is how the pseudocode would look like. Again, these three parameters are same. L and R would denote the range of the node, and I would denote the index of the array in which we are representing the tree, right? And X and Y denotes the actual query range. So we need to find the sum in between X and Y, right? So three conditions, either the node is not overlapping at all. So this is the first condition where we are saying that node is not overlapping at all. So if current node, so again, notice that current node cover the range L to R. So we are just checking whether X and Y completely lies outside of L comma R. So this is L comma R, right? So what we are checking is if Y is less than L or X is greater than R. So basically X is already less than equals to Y. So if Y is less than L, we know that this entire thing would be lying outside of L comma R, or if X is greater than R, we know again X comma Y would lie outside of L comma R. So that's the first condition. If it lies completely outside, we'll just return zero because we are trying to find the sum. Now, if we are not able to expand further, we know that this the contribution of this node would be 0 to the sum, right? Now, here, second thing is the node is fully overlapping. If it is fully overlapping, we know that we need to take that particular node completely. So this is the value of that node. So we just return from there. Otherwise, the node is partially overlapping, and for partially overlapping node, we will try to go in both left and right half. From the left half, we will query the same thing, right? And from right half, we will query the same thing. So finally, we will just add the contribution that we get from the left and right half, and that would be our final result, right? So hope this pseudocode also makes sense. And again, as this entire thing would run in order log n time, because we know that we will be touching at max 2 login nodes during this entire journey, right? Now let's look at the complete code once again. So this is how we will build the tree first in the first iteration. The first iteration will build the entire tree, and this would take order and time. So what we are doing here, we are simply iterating over. We want to build the tree for the range L comma R. So what we are saying is we will build the tree for L comma M and M plus 1 comma R, and then finally we will merge these two tree and figure out the value of the root node, right? So this is how we build the tree. After that, if we need to update the value of a particular index, we will simply follow the path to that particular index and update every node in between that we get. So the update logic would be exactly similar to how we have done in the like how we have done while building the tree, right? And finally, for the query, we have three condition: either the node is fully overlapping, or it is partially overlapping, or it is not overlapping at all. So if it is not overlapping, we will return 0. If it is if it is fully overlapping, we will return the value of that current node. If it is partially overlapping, we will go and try to visit both the halves, right? Now, this is how the code for a range sum and a point update segment tree would look like. Now, focus on the squared part here. So we are adding the nodes. So adding the nodes would give us the sum of a particular range. So let's say you have to find the max of a particular range. So if you have to find the max, you will just do replace this plus with a max, and every node in the path would contain the maximum value of the left and the right child, right? So whatever comes here, exact same thing would come here as well, because while updating, we need to take care of all the nodes that comes in the path. And finally, while querying, you have to take care of the case where the node is not overlapping at all. So here we return 0 because we know that we are doing summation. And if we add 0 to anything, the result would not change. But let's say you are doing a minimum, then you will not return 0, right? Because you know, for finding out minimum, 0 might change the result. So in case of minimum, you would return something that would not change your actual result, or that would not bias your results. So in case of minimum, you would be returning int max or some greater value, because you know you that value would not be biasing your result, because that is the largest value that will not exist in the array, right? So these values and these operators are the one that will change from based on the problem at hand. Otherwise, building the tree, updating a particular index and querying the range all of these would be exactly similar to every range query structure that you want to perform using segment trees, right? So now what's next? I would encourage you to try to get one problem submitted with this by writing by writing the entire code yourself. So just to start with, I would encourage you to solve this particular problem of Hacker Earth. This is very small problem, simple problem that exactly tells you to do what we just discussed. So you can try this out yourself, and then once you understand the concept and you have code this solution yourself, I will give you some practice problem in the description down below. You can try out that. And finally, I would encourage you to try to code the range update and point queries as well yourself. So basically, we have looked at how to do point updates, like updating up the index of a particular, updating the value of a particular index, and doing range queries, like finding out something in a range x to y. So I would encourage you to code range update and point queries using the exact same approach. Now, for those of you who know segment trees, you might be wondering that, okay, range update is possible using lazy propagation. You have to do lazy propagation to do range updates, but that is not actually required if the queries are point queries, right? So I would encourage you to code this particular thing yourself to understand, like how would you fit these two queries in this exact algorithm. So just to give you a hint, the exact solution would be very similar to how we do range updates in an array. So let's say you have to do a range update in an array, and you have to do a point queries at the end. So this, like, it is very similar to that particular problem where you just add to L and subtract from R minus 1. So, and finally to get the value of a particular index, you just do a prefix sum. So this problem can be boiled down to this exact same problem, and you can apply this exact same trick that we just discussed to solve this particular problem. So there is a nice application to the exact same concept of range update and point queries. You can try to solve this particular problem of code chef. This exactly will, like, you will be able to apply this exact same concept in that particular problem, right? Again, you don't need to use lazy propagation here. You can solve it with the concept that we just discussed in this video. So with that, we will stop here for now. In the next video, I would be starting with lazy propagation, and like we'll first see the solution of this particular problem, and then we will be starting with the lazy propagation, or how to exactly do range updates in a segment tree. Up till then, I would again encourage you to code this solution yourself and try to solve all the like how as much practice problem as you want uh, to strengthen your understanding of the segment trees. So hope you like the video. If you understand it, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.